Okay.
So, welcome everybody to our Gamma seminar. Today we have the pleasure to guest Alessandro Arsie from the University of Toledo in the United States, who is going to talk about an introduction to Dirac geometry and reduction schemes for concurrent direct structures. So, Alessandro, thank you very much for accepting our invitation. It's a pleasure to have you here, and the floor is yours. Please, go ahead.
Well, thank you very much for the kind invitation. And so I'm going to provide an introduction to Dirac geometry from a certain perspective, and also talk about some recent results obtained by with my collaborators, Dan Agüero, Pedro Frilich, and Igor Mencatini. And here are my, that's the most important slide of the talk, my wonderful collaborators. And so the plan, I mean, before telling you the plan, I really like very much this quote, especially for this kind of mathematics. It says, "The limits of my language mean the limits of my world." It's a quote by Wittgenstein. And as you will see, it's very appropriate because Dirac geometry is a simultaneous generalization of Poisson, symplectic, pre-symplectic, and other geometric structures. And for instance, it's very well known that if you have a Poisson manifold and you take a submanifold, you have different kinds of submanifolds you can choose in a Poisson manifold. And according to the class of submanifold you choose, you have different possible linearity structures. And this makes a very complicated set of classifications, so to speak. But if you speak instead of, Dirac structure, you will say simply that any submanifold of a Poisson manifold inherits a Dirac structure, and without any problem, okay? So without having to specify different conditions. And of course, this Dirac structure will be different, because they might be the graph of a Poisson structure or something else, but it's a one shot, so to speak. Okay, so the plan of the talk is this. So I will go over, but this very, very briefly, although I have maybe 20 slides about this, Dirac original idea and current interpretation. Then I want to give examples of Dirac structures and the two product operations, namely tangential and cotangential product. This is a bit technical, so I will just tell you that they exist, under some assumptions. And the core, so to speak, of my talk will be this one. And this is also related to, also this, but this I don't think I will have time, is related to the work that we have been doing. And you will see what this means. In particular, we'll be able to extend the Marsden-Ratiu reduction to the class of Dirac manifolds, and discover that Marsden-Ratiu reduction is really not simply a reduction, but is a reduction that preserves compatibility of two Dirac structures, okay? This was essentially observed by Magri, Casati, Magri, and Pedroni in the case of Poisson structures, but we extend it to the case of Dirac structures. Okay, so let me actually start. So here there are lots of slides, and I just want to say this. So when you have a Poisson manifold, a symplectic manifold, if you impose some constraints, then the constraints in general will not preserve your environmental geometric structure. And so this, of course, creates problems that were already realized by Dirac. And Dirac classify the constraints in first class and second class, okay? And one can interpret them geometrically. So here there is all the description about this, which I'm going to skip. As you see, I'm skipping a lot here, just because I want to start with just an example to explain what I mean. But probably, to you guys, it's very well known this. But suppose that you start with R3, and we coordinate X, Y, and Z, and you take this closed form, which is of course not symplectic because it has a kernel, not trivial kernel. And now you set up the Hamilton's equation, okay? And if you take the equality on both sides, you have this equality. And this equality tells you that not all function, okay, can produce corresponding Hamiltonian vector fields in this case, because for instance you have that hz has to vanish, since on this side there is no dz. Okay, so here is the important point, that existence fails unless hz is 0. And uniqueness also fails because one might add to the, so if you have a function that doesn't have any, for which hz is identically 0, the partial derivative with respect to z, then you can add to the Hamiltonian vector field x, you can add any multiple of the dz and still get a vector field that satisfies the Hamilton's equation, the equation that defines Hamiltonian vector fields. So this is exactly the kind of phenomenon that Dirac geometry was designed to encode naturally, okay? And we will see that in a moment. Well, I mean, let me also, so here I will start with starting building up the definition of a Dirac structure, okay? So the environment is, so a Dirac structure is essentially a subbundle of a certain bundle, and this bundle is what is called the generalized tangent bundle. So the generalized tangent bundle is just the direct sum, it's usually indicated in this way, is the direct sum of the tangent plus the cotangent. And elements, we write elements of the generalized tangent bundle, sometimes it's also called Pontryagin bundle, as x plus alpha, where x is a vector field and alpha is a one form. So the idea is simple, that vectors describe direction of motions and covectors describe momenta, constraints, Hamiltonians, and reactions, okay? Okay, on this bundle, okay, over M, there is a nice non-degenerate bilinear symmetric form, okay? So this is a non-degenerate, symmetric and bilinear. And this is not positive definite, okay? It has signature, so if the dimension of M is n, it has signature plus one n times and minus one. So as you see, you take simply a vector and a covector, and you pair them in such a way that this covector acts on y and this other covector acts on x. Okay, so you get this number. Okay, and so it has, as I said, a split signature. And this pairing is the linear algebraic structure behind Dirac geometry. So this allows us to talk about isotropic and Lagrange subbundle. So now I'm going to define, of course, for you what this means. So if you have, first of all, let me say that if you have a subbundle of the generalized tangent bundle, then the orthogonal, when I write the orthogonal, is the orthogonal with respect to this canonical pairing, okay? And in particular, if E is a subbundle with a node with E circle its annihilator. Okay, with this definition, so a subbundle L in the generalized tangent bundle is called isotropic. So it's similar to the notion of isotropic subspace of a symplectic vector space, except that here instead, in the case of the symplectic form, you have something skew symmetric. Here you have something symmetric, but it works precisely because it has signature plus one minus n, let's say split signature. So it's isotropic if L is contained in its orthogonal. So example of isotropic subbundle inside the generalized tangent bundle are the tangent bundle itself, the cotangent bundle, and F, where F is a subbundle of Tm, okay? In this case, F perp is given by the tangent bundle plus the annihilator. And as you can see immediately, that F is contained in F perp in this case. So there is no problem. So this is isotropic. And it is called the Lagrangian if it is maximally isotropic. So indeed, Tm and T star M are maximally isotropic. Okay, so this is the condition for being Lagrangian. So since the rank of the generalized tangent bundle is 2 times the dimension of the manifold, a Lagrange subbundle has necessarily rank equal to the dimension of M. And notice the funny, so let's see, there's examples that are not exactly like this, okay? So take any two form, so it doesn't need to be closed, okay? And take the graph of omega. So the graph of omega is simply given by, you take all the vector, the tangent vector in vector fields, okay? And you take a V plus, you contract omega with V. Of course, this is, this object here is an element of is a section of this theorem. And it turns out that if you do the computation, this is indeed a Lagrangian, okay? This is a Lagrange subbundle. So the graph of omega, the graph of omega perp is equal to the graph of omega. And not only this, but if you have a graph from Tm to star m, so you have an operator, say, from Tm to star m, whose graph is Lagrangian, it necessarily comes from a two form. So the fact that this is Lagrangian is equivalent to the fact that this is a two form. And the same is true for a bivector, okay? So if you have a bivector, you can set up the graph of the bivector, and this is Lagrangian precisely for the same reason. So what the Lagrangianity here encodes is simply the fact that this map and the map omega flat, okay, they come from a skew symmetric object. So that's essentially what the condition of being Lagrangian means here. Okay, now so far so good. Let me notice that often in mechanics, especially people that do what is called non-holonomic mechanics, they mean Dirac structure, what here are called Lagrangian subbundle. Okay, so so they are weaker, as you will see. They are weaker than the usual Dirac structure one it deals with in geometry. Okay, so far this is still not for us at least a Dirac structure, something which is Lagrange is not Dirac enough. It means that Dirac is not Dirac in our sense, okay? And so on section of the tangent plus cotangent bundle, one can define what is called a Dorfman bracket, okay? So Dorfman bracket, you take a vector fields in the form, a vector fields in the form, you take the commutator of the vector field, and then you take this bizarre expression, okay, which is the Lie derivative of beta with respect to x. So again, notice that this is acting on this, and this is acting on this. And you take the differential, the stereo differential of alpha, and you contract with y. So there is also a skew symmetrization, which is called the courant bracket, but actually it's more convenient to work with the Dorfman bracket. So neither of them, I mean, you know, this bracket is clearly not skew symmetric, the Dorfman bracket. This one is skew symmetric, but neither of them is a Lie bracket, because this one, the courant bracket fails the Jacobi identity, okay? However, the Dorfman bracket is kind of magic because it controls, I mean, I won't go over this much in detail, but it controls when a form is closed, when a bivector is Poisson, when a regular foliation is integrable, when a Lagrange subbundle is Dirac, okay, which is what we are interested in, and where endomorphism of Tm is new noise, okay? So everything can be expressed through, all these conditions can be expressed in terms of the Dorfman bracket. Okay, so now we finally arrive at the notion of Dirac structure. So Dirac structure, this is due to Courant, and who was a PhD student of Alan Einstein, on M is a Lagrange subbundle of our beloved generalized tangent bundle, such that if you take the Dorfman bracket to two sections of L, you end up in L. Okay, so that's the so it's a closure under Dorfman bracket of section of L. Okay, so one interesting point is that if you, so as I said, Dorfman bracket is not a Lie bracket, but it becomes a Lie bracket when it is restricted to section of a Dirac structure, okay? So if you restrict the Dorfman bracket to sections of the Dirac structure, then it becomes a Lie algebra bracket. The reason is that if you take the sum of, so you take the, you take E1, E2, where E1, E2 are section of L, and or section in general, the generalized tangent bundle, you play the Dorfman bracket, you sum the same with the order switched, and you get a D of the pairing, the linear algebra pairing between E1 and E2. Since for section, since L is a Lagrangian subbundle, okay, for section of a Lagrangian subbundle, this pairing is identically 0 because it's Lagrangian. And so this term is going to disappear, and this will make the Dorfman bracket into a Lie bracket, okay, for section of the Dirac structures. So there are two layers in the definition. One is the maximal isotropicity, which means being Lagrangian, which is just a linear algebra condition, and involutivity under Dorfman bracket, which is a differential geometric condition. Okay, so now you might say, well, how these relate to mechanics or dynamics. So the idea is this. So this is the setup. So not all functions on a Dirac manifolds are admissible, okay? They are observable, let's put it this way. So a function is called admissible if, let's say, there exists xf, which is a section of the tangent bundle, such that xf plus df is a section of your Dirac structure, okay? And for admissible function, one can define a bracket, which is this. And this bracket is indeed a Poisson bracket, okay? However, so first of all, on the Dirac manifold, you cannot bracket any two functions, okay? You can only bracket a function for which there exists an xf, such that xf plus df is a section of your L. And for this function, there is a Poisson bracket. And the vector field xf is not uniquely defined. Okay, so you can add to this xf any vector that lies in L intersected Tm. So here, just a remark that when you will see people writing this, they really mean this. Okay, except that to make things shorter, they don't write like this, and they follow the standard notation, okay, which is to skip this part. But so basically, you're looking for elements section of L that are of the form z plus 0, okay, gamma L. And it's not difficult to see that if you do this, if you evaluate this z on a function, on an admissible function, okay, this is going to not affect the bracket, because the reason is very simple. If you say G is admissible, then this means that exists xg plus dg in gamma L. Now, z plus 0 is in gamma L, but sections of gamma L is isotropic, is a Lagrangian, right? So if you pair with the pairing that I gave you before, xg plus dg, z plus 0, this is exactly, here this guy acts on this form, this form, which is 0, acts on this guy, so there is nothing to do. And these one are pairs, so this is exactly z acting on g. But this is 0 because L is equal to L purple. Okay, so ZG you don't see if you add. So this is kind of gauge. Okay, so you can add these vector fields for free, and this will not change the dynamic. Okay, so the three paradigmatic examples of Dirac structure are exactly. So remember that if you have a two form, this produces a Lagrangian subbundle. If you have a bivector, this produces a Lagrangian subbundle, okay? But in order to get the Dirac structure, you need involutivity. So at this level, involutivity is read exactly in terms of the closeness of two form. So this is equivalent to say that this is a Dirac structure. And the vanishing of the Schouten bracket for pi is equivalent, so saying that pi is a Poisson tensor is equivalent again to say that this is a Dirac structure. And this example here is also very important. So let me, especially for what comes next. So here F is just say a subbundle of Tm, okay, and saying that this is a Dirac structure is equivalent to say that F produces a foliation, okay. So that's the same thing. So you see how powerful is this unifying language, okay. So far it's just the unifying language, but it's pretty cool in its versatility, since all these apparently different things are exactly the same thing, okay. It's like a grand unification of certain things, of certain structures. Yeah, so here I'm just reiterating what I said, that if you have a two form, this is automatically a Lagrangian subbundle, and it is Dirac if and only if the two form is closed. And furthermore, if you are given a Dirac structure, okay, suppose you are given a Dirac structure, this is the graph of a closed two form if and only if this holds true, okay. And let me show you why this is. I think I have time. Yeah. So because I think this is instructive. So if you have T, let's say T star M plus Tm, here you have the projection to Tm. So you have an exact sequence. Okay, and your L lives inside here. Now, if you restrict the projection, so PT is just the projection to the tangent bundle. So you restrict your PT to L. This is in general not anymore exact, right? I mean, that's no reason why it should give you the entire Tm. But so here the kernel of PT is of course just T star M, or better, to be more precise, it will be T star M direct sum 0. Okay, so if the kernel then of PT, so here I put the kernel of PT restricted to L. This is just what? This is just, if you look at it, this is just L intersected T star M. So saying that this condition holds means that this is 0. And if this is 0, since this has rank n, the dimension of M, and this has rank n because it's Lagrangian, this means that this map is an isomorphism, okay? This map is an isomorphism. So I can invert this map and produce, essentially, this allows you to write L as the graph of a map from Tm to T star M. And this map necessarily is a two form, okay? I mean, as the property that can be described by a two form because L is Lagrangian. And then the fact that L is Dirac tells you that this two form is closed. Okay, so that's exactly the essentially the proof of this fact. Okay, and one can play the same game with Poisson tensor. Okay, so if you take any bivector, this is Lagrangian. And this is Dirac if and only if pi is Poisson. And again, like before, if you are given a Dirac structure, how do you recognize is the graph of a Poisson tensor? Well, simply look at L intersected Tm. If this is 0, then you are being given the graph of a Poisson tensor. If it is not, then it's not the graph of a Poisson tensor. Okay. And there is a similar. Well, let me do this example because this is cool. So suppose that you have the following singular Poisson tensor. Okay, so it's a tensor in R3, actually in R3 minus the locus where z is equal to 0, because of course this is not defined when z is equal to 0. But however, you can view it as a graph. Okay, so constructing the corresponding Dirac structure, you can show that this guy here here, is equivalent to, it's equivalent while it is defined, to a smooth and everywhere defined Dirac structure on R3, which is the span of this element. Okay, and so essentially this tells you that in some situation, not always, of course, because it depends on the singularity, Dirac structures are able to describe singular Poisson tensors or singular pre-symplectic tensor, okay, and are able to describe as smooth and everywhere defined. Okay, so that's a nice possibility. So there is a similar how to say, characterization of Dirac structure that comes from a foliation. Okay, I listed here, but I mean you don't need to. We don't need this. Like I just listed because it's a nice exercise. Okay, and okay, so now we have a Dirac structure. We know what they are. We have examples of these things, and we would like to compare them to Poisson structures. So we know that given a Poisson structure is essentially equivalent to give a foliation by symplectic manifolds, okay? And so is there something similar to this point of view for Dirac structures? And the answer is yes. So it works in this way. You take a Dirac structure, and then one can show that if you project the Dirac structure on the tangent bundle, you have a distribution. Okay, so that's why I say generalized foliation, because this is in general not a subbundle because the rank changes, but you have a distribution which is integrable in a generalized sense because it's not a constant rank distribution, and each leaf of these foliation, generalized foliations, carries a closed-to form. Okay, so there is a closed-to form which is this is leaf-wise closed. Okay, and it is defined in this bizarre way. So if you fix a leaf, okay, fix a leaf, and then takes a tangent vector to the leaf, and you define our two form. Okay, so this two form omega O of xy is defined in this way. So you have to look. You take vector tangent to the leaf. Okay, since this vector belongs to the projection to T of L, this means that there exist y and b, alpha and beta, such that x plus alpha and y plus beta are section of the Dirac structure. Very well. When you do this, you define omega O xy to be alpha y. Okay, this seems kind of, we say there is lots of ambiguity here because in general, if you fix x, there are many covectors for which x plus alpha belongs to L, but you can show that if you choose another one, the form is well defined. Okay, so in the sense that the result doesn't depend on the choice. And not only this, precisely because gamma L is isotropic, so the pairing between x plus alpha and y plus beta is identically 0. So this, if you write it down, this means exactly that beta x plus alpha y is 0. So, and as you see, alpha y is equal to minus beta x. And so you can write these precisely in this way. So this shows you that this is skew symmetric. Then it takes a bit of work. I mean, not much, but it takes some work to show that this is closed. Okay. But the upshot is that a Dirac structure is globally encoded by a pre-symplectic foliation. Okay. So in general, these closed-to form are not symplectic. So they have a kernel. Okay. And the kernel of this pre-symplectic form is exactly L intersected Tm, okay? So if you want to know how big is the kernel of this guy, just look at L intersected Tm, and this will give you the kernel. Questions so far so good? If you have questions, please feel free to interrupt me at any time, okay?
Alessandro, everything is clear, and several of these things have been before, so it's okay.
Okay.
It's very clear, but yeah,
okay,
it's very fun. I'm not saying anything because I'm following, but it's everything is.
No, that's good because I know that some people already talk about Dirac structure and the stamina, but you know, sometimes repetita juvent, as they used to say in Latin. You know, like
it's a good thing, Alessandro, to repeat things in my opinion. So everything goes fine. Thank you.
You're welcome. Okay, so this is mostly a notational thing in the sense that suppose you have a Dirac structure on M and omega is a closed form, then you can add omega, so to speak, to the covector part of L, okay, and obtain what is called the gauge transform of L by omega, which is defined in this way. And similarly, if pi is a Poisson tensor on M, then you get the gauge transform of L by pi. Here you don't need, actually, for this to be defined, you don't need omega to be closed or pi to be a Poisson tensor, and you need L to be Dirac. So, for instance, if L is a Lagrange sub-bundle and omega is just a closed form, sorry, a two-form, not a closed form, a two-form, you can anyway construct the gauge transform of L by omega. Okay, and the same is true in this case. Why this is useful? Because there is this, so this is not super well known, this result here. I mean, it's folklore in the sense that, you know, people working this stuff knows it, but it's not super well known, which I think it's a pity because it's very useful. And it says the following thing. So suppose if you have a Lagrange sub-bundle on M, then up to an open dense set, okay, you can always write L restricted. So there exists an open dense subset. So generically, basically on M, L restricted of this subset is equal to the gauge transform by omega, where omega is just a smooth two form, so it's not closed in general, of the gauge transform by omega of the graph of E, where E is the projection of L to U to the tangent bundle. Okay, so E here is just a distribution inside the tangent bundle, and you can construct the graph of this E, and the graph of E, let me remind you, is just graph of E is just E plus its annihilator. Okay. And then you gauge transform like I described here. So you add essentially on the covector part, this part here by omega. And you can do the same game using a covector, a bivector, sorry. But this time you have to take the projection of L restricted to U on the cotangent bundle, okay? So you define F. Now the graph of F, it looks funny because now F is not a distribution inside Tm, right? Is inside T star M. So it doesn't make much sense to talk about the distribution, but its annihilator is going to be a distribution, okay? And so you define the graph of F, and then you perform a gauge transform by pi. Okay, so there exists, so the statement is this, there exists a smooth two form and a smooth bivector. So up to restricting to an open dense set, any Lagrange sub-bundle can be written as the graph of a foliation, put in this way, either using a two form or a bivector. And this tells us also when L is Dirac, okay? So L is Dirac, so such an L is Dirac precisely when E is involutive, okay? So this is distribution. This doesn't need to be involutive in this setup when L is Lagrange. But if L is Dirac, then necessarily E is involutive and omega is Leaf-Y closed, okay? And the kernel of omega is precisely, like I told you before, is precisely the intersection of value with Tm. I should have written Tu really, because we are, so this is Tu really, but and instead, if you use this other description, okay, then you have that L is Dirac if and only if these three conditions are are satisfied. So you want that the annihilator of f this time, because the annihilator of f lives inside Tm, is involutive. You want that so this is the Dorfman bracket twisted by pi. What does it mean? It means this expression here, pi plus, actually should I pi like this? Okay, this is the Dorfman bracket, and here you put the Dorfman bracket, so acting on forms, okay, twisted by pi. So there is also another term which is minus pi this, but the Dorfman bracket, when it's applied to just pure forms, vanishes, so this term is not there. And you have this condition here. And these other condition, okay? These other condition can be expressed also in another way. This is the Schouten bracket, but it can be expressed also using the noise torsion of pi, essentially. And saying that the noise torsion of pi is valued in gamma f naught. It's the same thing. But the important point is that there is, so what this is telling you is that up to an open dense set, your Dirac structure, no matter how complicated it is really the graph of a foliation modified by omega, close to form, close along the leaves, not globally closed, or the graph of a foliation twisted by pi, where pi is not Poisson everywhere, but is Poisson essentially evaluated, so satisfy Jacobi identity, but only when it is evaluated on function whose differential lives in f. Okay, so that's the
Alessandro.
Yeah.
Yes, one question, because indeed, as much as I remember, this didn't appear here during our seminar so far, but I have applied it a couple of times, and indeed, as you said, it's very useful. But could you comment where you apply this, or where you can find this?
Where can I apply, or when can I find it?
In which applications, in which theories, or which aim can you use this?
So, for instance, we use it. I can tell you where we use it. So, since I can tell you where we use it, because so if you want to prove, for instance, that something is closed under the what's called under the Dorfman bracket, okay, then it's convenient to have a representation of L in these terms, okay, and especially when you want to prove that, so as you will see later, when you have two Dirac structures that are compatible in a certain sense, okay, and you want to prove that certain sections are closed under the Dirac, the Dorfman bracket, then what happens is that you put yourself in an open dense subset where it's easier to describe essentially the sections of L or another Dirac structures. And then if you can prove that in this open dense subset, for instance, you have closure under the Dorfman bracket, or better, a certain tensor, which is the courant tensor, vanishes, then it has to vanish everywhere on the manifold, because this is an open dense subset, and then you have your result everywhere. Okay, so that's a typical application, I would say. Okay. I hope I answer your question.
Yeah, sure.
So
yeah, sure. Thank you. Please go ahead.
Okay, so now there is an unpleasant, I say unpleasant because this stuff, I don't want to spend too much time on this. So when you have a smooth map, okay, you can transfer, let's say that this is not necessarily Dirac. Dirac is just Lagrangian, okay? So this is the fiber over the point f of x of a Lagrangian subbundle over n, and you can pull it back. So there is a formula. I'm not going to go through this because it's a bit involved. And the same, there is something called the push forward, inverse image and direct images. Okay, they are denoted this way because this is different in general. So this is different than pulling back the bundle ln. Okay, so that's not the same as pulling back the bundle of LM. Okay, so that's why there is a specific notation, not because we want to be fancy, but really just because it has a different meaning. And let me just say that, so I will skip this part because here anyway there is some background for those who want to read it. So the basic fact is this, that if you have a smooth map between smooth manifolds, okay, then if Ln, so if you have a Dirac structure on N, then and the inverse image is a smooth subbundle, then this is Dirac, okay? So you need to check that this is smooth subbundle. And if you have a Dirac structure on M, and F is an invariant, so LM is an F invariant Dirac structure, so it's a condition. F is surjective, okay? Then and if this guy is smooth subbundle, then the direct image is Dirac too. Okay, so these are some technical things, but you know, we want you know, for a seminar that's not something we want to go with. And for this, let me just state this thing. So forget about this. I mean, don't look at this. Just take a isotropic family. By isotropic family, I mean simply a choice of isotropic subspace inside the TM at each point. It doesn't need to be smooth, continuous, you know, like just an isotropic family. Then for us, this will be, of course, a subbundle, but just take an isotropic family. And then if you have a Lagrangian family, again, the Lagrangian family is just a choice of Lagrangian subspace at each point, okay? You have that this object here, which is called the stretch of L by K, okay? This is called the stretch of L by K, is also Lagrangian. And here's the proof. I mean, as you see, the proof is just one line, but I won't go over it. Okay, and it's called the stretch Lagrangian family. Is the one which is closest to the original L among all those Lagrangian subfamily that contains K. Okay, so if you have a Lagrangian family that doesn't contain K, and you want to obtain one, well, the minimal effort you have to make, you know, the minimum amount of work is to do this, to take L intersecting K perp and add K, okay? Okay, so there is a famous result due Paulette Lieberman, and maybe you know it in the classical form, but let me state it directly in the Dirac form, so in the generalized form. And the theorem is the following. So suppose that you have a smooth surjective submersion with connective fibers, defining a simple foliation. Okay, and of course I forgot an assumption that LM is a Dirac structure, Dirac on M. Okay, so then you can project down LM to a Dirac structure on Y, if and only if the following happens. If you take LM and you stretch it by F, where F is the fiber, so F here is just the kernel of P star, okay? So these are just the tangent, essentially the tangent bundle to the fibers. So if you stretch LM by F, so you perform this operation, the result is Dirac, okay? So you can check that something projects down to a Dirac structure downstairs, precisely if and only if this happens. This I will skip it here. There is a worked out example that I leave it to your students actually, and yeah, one can play the same game with the Poisson action, okay? And so if you take the special case in which LM is the graph of a Poisson tensor, and E, and you have a Lie group acting by Poisson automorphism with orbits defining simple foliation, and E is the infinitesimal action distribution, then you can check that this guy here is indeed Dirac, okay? So this guy here is indeed Dirac, and therefore this Dirac structure reduces to Dirac structure downstairs, which is indeed Poisson in this case. Okay, so now I want to describe two two tools, okay? I mean, two operations that you perform, not just on the Dirac structure, but on Lagrangian family, really. But let's discuss them in this way. And so I will keep it simple. Suppose that you have two Dirac structures, okay? And you take a section of L and a section of R, and you form what is called a tangential product whenever the vector part is the same, okay? So if the vector part is the same, then you say, okay, I take the common vector and I add the covectors, okay? This is called the tangential product. You will see in a moment what is its meaning in the case of forms, in the case of foliations, you know, this kind of thing. The nice thing about this is that if these guys are Dirac, then the tangential product is Dirac if and only if it is smooth, okay? So once it is smooth, closure under Dorfman bracket is automatic, okay? Good. Now, there is a similar gadget. Well, here I already wrote an interpretation, but, you know, like I skip this. A similar gadget is the cotangent product. So the cotangent product, this time you have two sections of L, one section of L and one section of R, sorry. L and R are Dirac structure here that have they have a common covector. So the covector part is the same. And then you sum the vector part, okay? So, I mean, it seems pretty, you know, not terribly difficult or ingenious, but actually this is actually a very ingenious thing. And so the covector part is shared while the vector parts are. So for cotangent product, okay, so if L and R are Dirac, then the cotangent product might fail to be smooth, and even if it is smooth, it might fail to be involutive, to be closed under Dorfman bracket, okay? So this is less well behaved than the tangential product. And you see, you might ask, why there is this mismatch between the two? Because, you know, after all, we are not that we are making something much different, right? Well, the mismatch is due to the fact that the Dorfman bracket doesn't treat symmetrically forms and vectors if you look at it, right? So examples are the following. So it's easy to see why even if it is smooth, it is not guaranteed to be involutive. Because, for instance, if you take the cotangential product of the graph of two Poisson structure, this is exactly the graph of the sum of the two Poisson structures. So this is smooth, but there is no guarantee that this guy is going to be Poisson, which is exactly the involutivity condition. You know very well, better than me, that if you sum two Poisson tensors, this might really very fail to be Poisson, right? So as you see here, this guy is always smooth, but in this example, okay, but fails to, I mean, in general, fails to be involutive. On the other hand, if you take the tangential product of the graph of two forms, well, this is very nice behaved because this is the graph of the sum of the two forms. And of course, if omega L and omega R are closed, omega L plus omega R is closed. So this is automatically Dirac, right? This one is automatically Dirac. So no problem. In the case of foliation, okay, so suppose that you have two foliations, FL and FR, well, the cotangential product is just the graph of the sum. And of course, here you enter exactly the same problem of closure under bracket because the sum of two foliations is not necessarily a foliation, right? I mean, there is no reason why they should be closed under the commutator of vector fields. But if you take the tangential product of the graph of two foliations, then you get the graph of the intersection of the two foliations. Now, if the intersection is constant rank, say, then you are in a good situation and everything works fine in this case. So this tells you why there is a mismatch between tangential and cotangential product. Okay, so now we need this definition. This definition is very simple. So suppose that you have two Dirac structure, you say that they concur if their cotangential product is a Dirac structure. So that's the notion of compatibility. So that's exactly similar to being bi-Hamiltonian, because you see here, when this is Poisson and this is Poisson, which means when this one is Poisson and this one is Poisson, I mean, pi L is Poisson and pi R is Poisson, so these are Dirac. Their cotangential product is Dirac precisely when these are compatible Poisson tensor, okay? And so it is natural. Yeah.
So it looks familiar to like the pullback generalized bundle? Is it this kind of thing?
Pardon?
So this tangential and cotangential product, is there any relation with like with the pullback bundle or something like that pullback construction or something like this?
The one that I defined before with this one, or
the tangential and cotangential products you defined like
so you're asking me if the cotangential product or the tangential product are related to the inverse image and forward image or not? Or not?
Yeah. Okay. Yes.
No, they are not. They are not related to those, but
okay.
they are related. They are related to something else, right? Because if you look, so L is let's say that L is inside the Tm plus T star M, and here you have M, and here you have R, which lives inside the Tm plus T star M, right? Now, what you can do is to form a fiber product over. So, for instance, if you do over T star M, I think you have to take. Let me think. Yeah. So actually, this is something like this, because you see the problem is this, that you take. So let me take T star M. So I can form the fiber product over T star M of these two. Okay. Now this one should correspond to this, but the problem is that so I'm not guaranteeing that this map have constant rank. So this map here and this map here necessarily don't have constant rank, right? So and that creates a little problem. So that's why, but essentially, morally, you can express these in terms of a form like this, and similarly, you can express the tangent bundle as the tangent product as a fiber product over Tm. Okay, so that's probably what you had in mind, I think, more than.
Thank you.
And we say inside that they concur weakly if their cotangent product is merely involutive, meaning closed under Dorfman bracket, even though it doesn't need to be smooth, okay, or constant rank. So this is the right generalization of the notion of commutativity between the Poisson structures. So going back to Lieberman theorem, okay. So if you have a simple foliation with quotient B, and you have a Dirac structure, Dirac on M, then, so Lieberman theorem says that Lm descends to B, the generalization of Lieberman theorem to Dirac structure, saying that Lm descends to B, if and only if Lm stretch with F is Dirac, if and only if Lm concurs with the graph of F. Okay, so it's I mean, this is just a way to restate the same thing. Okay, so now let me come in the last 5 minutes or so. Let me come to our contribution, okay? Because so far I talk about just the general things, okay? And so our contribution has two types. So one, we have the following problem: we have a Dirac structure. Actually, it's better if I write it like this.
Sorry, Alessandro.
Yeah, tell me.
Don't worry if you take 5-10 minutes more. That
okay.
It's okay, perfectly okay.
Yeah. So the reduction triangle is this. So suppose that you have a Dirac structure on M. Okay, so this is Dirac, and you have an embedded submanifold, and then you have a smooth submersion, a smooth surjective submersion. Okay, and the question is, so there are two kinds of questions. One, what is the minimal set of conditions you need to transfer this Dirac structure to Dirac structure here? Okay, and can we do this preserving concurrence? Namely, if we have compatible concurrent Dirac structure on M, can we transfer them concurrently to Y? Okay, so first to discuss the minimal reduction, okay? The minimal set of conditions to achieve this. And the minimal set condition to achieve this, I mean, this is just what we mean by minimal reduction, okay? We say that LM Dirac reduces to Y if this structure here is Dirac on Y. So the minimal reduction procedure is simply you take restrictions to X, taking the inverse image, and then you take the projection to Y by Dirac image. So we are not requiring that in this process, the inverse image of LM to X is Dirac on X, okay? So this is important. We are not requiring this. And maybe let me just read the result. Well, the result, yes, I mean, the result is this. So let me just state the result. I have to tell you what is K. So K here is F plus N star X, where F is just the kernel of pi, where pi is pi star, where you have X, I, and then you have M, and here you have P, pi, and here you have P, sorry, not pi, and here you have Y. Okay, so this is a isotropic subbundle inside the generalized tangent bundle of M. Actually, no, restricted to X. And our first result is that LM reduces to Y if and only if this is Dirac. Okay, so that's the minimal reduction, which is characterized entirely in terms of essentially the environment. Okay, and the only information about X is contained in this guy here. Okay, however, so here I put some advertisements, so to speak, some marketing. So okay, this is unfortunately this minimal reduction does not control concurrence, meaning if you have two concurring Dirac structure in M, so they describe compatible, let's say, Dirac structure, then suppose they minimally reduce to Y, so this is Dirac and this is Dirac, okay, then the reduced structures downstairs on Y are not guaranteed to concur, or even to be weakly concurring. So the cotangential product of the reduced structures downstairs is not involutive in general, okay? So the minimal reduction transfer structure, but is not necessarily, but not necessarily their compatibility. Okay, and so here there is an example that you can work for. I mean, you can work through it. And so this, how to say, pointed us to look for a reduction in which concurrence is preserved, or weak concurrence. And this essentially was suggested by an observation, actually, a paper by Casati Pedroni, that observed that Marsden-Ratiu reduction is Hamiltonian in nature, in the following sense, that every time you have a Hamiltonian structure, this automatically provides Marsden-Ratiu reduction data, okay? And so in our original triangle, which is this one, and so we have our X, I, M, and here you have the projection, okay? So now we are looking for a different reduction scheme satisfying four requirements. So it implies minimal Dirac reduction, okay? So of course it has to be stronger than minimal Dirac, stronger in the sense is more specific. So it is contained in the set of minimal reduction, Dirac reduction. It reduces to Marsden-Ratiu when you apply to Poisson, to graph of Poisson tensors, okay? It reduces to Lieberman theorem when you don't have a submanifold, but your submanifold X is the entire M, okay? And it preserves concurrence, at least weakly, okay? And in order to do this, we need an additional data, which is called the witness. So we call it the witness because it's a witness of concurrent. Okay.
Sorry,
yes.
Alessandro.
Yes.
It allows you to retrieve another Marsden-Ratiu reduction in other cases, because with Dirac you can also describe all the types of geometric structures. Yeah. So it's you can retrieve all the cases. For example, I know Jacobi on the Dirac structure is related to the Jacobi structure, or to, I don't know, to almost conformally symplectic or something like that?
Well, I mean, I don't know. So I don't know the Marsden-Ratiu for Jacobi, okay, or for conformally symplectic. This, I mean, you might be right. Actually, this is something to look at, because I mean, I don't know if they exist already, and that it will be interesting to see how you put them in this framework. Okay, so that's but this is, as you will see, this is actually very natural, but yeah, I don't know actually, because I don't know myself actually Marsden-Ratiu reduction for Jacobi structures, or for
you know, you have for almost everything right now, so it could be a good thing, because it's you can gather together many things that now they are very you know, different settings. It's kind of interesting. Let me know at the very end where you have these results published or done, because I
no, as soon as you know, I'm there pushing and being pushed. So okay, so let me just recall the maybe I don't know. I have 5 minutes, 10 minutes, right? Yeah, I don't want to. So I mean, here there is a recall of Marsden-Ratiu theorem, okay, and conditions, and the essential point is that if you look at, you know, Marsden-Ratiu paper, you have a subbundle of the tangent bundle of M restricted to X, okay, and then you have this subbundle induces a foliation, an integrable foliation, simple foliation on X. So you have the leaf space and the corresponding submersion, and you have some conditions that are given in the 2 and 3 that are given in the original paper. Okay, this condition can be expressed in other forms. Okay, can be reformulated in other way, and so this E will play the role of what we call a witness. Okay, so you will see what it is. It's here. So let me point out that Liu, Weinstein, and Xu in this paper, which is pretty old actually, I mean, pretty old, 1997, asked to interpret and extend Marsden-Ratiu reduction in terms of Dirac geometry. So here we provide our solutions to this. So we have again an embedding of X in M. We have the projection to Y, and so you assume that you have a subbundle of Tm restricted to X that induces on X a simple foliation. Okay, so meaning this is a bundle of an integrable distribution, regular distribution, say, of inside Tx, and so such as a bundle is called adapted. Okay, because it gives to this triangle, and we say that E is a witness for LM satisfy these 3 conditions. Okay. So this is a vector bundle. This is a stretch of LM Vk, and K, let me remind you, is just F plus n star, the conormal. Okay. Then you want this other condition and this other condition. Okay, so these 3 conditions, let me just say what they mean here. So this is a regularity condition, this is an integrability condition, and this is a compatibility between E and the ambient Dirac structure and the conormal geometry of X. Okay, so I cannot you know, go over this in detail, but these 3 conditions are what defines a witness. Okay. And so here there are some details actually about, but the essential point is that if a witness exists for LM, then LM Dirac reduces to Y. Okay, and we call this reduction in presence of a witness a concurrent reduction or reduction with a witness. So concurrent reduction implies minimal reduction, which is the first required property. The second is that if LM is the graph of pi m, is the graph of Poisson structure, then E is a witness for the graph of pi m, if and only if E satisfies the Marsden-Ratiu conditions. Okay, so this generalizes exactly Marsden-Ratiu to this Dirac setup. It recovers Lieberman theorem. Okay, so in particular, it interpolates between Marsden-Ratiu and Lieberman, if you want, and it's compatible with concurrence. I wrote it. Yeah, here. So if LM and RM are weakly concurring Dirac structure and E is a witness for both, then their reduction concur weakly. Okay. So at this point, and I'm going to finish here, really, I don't want to abuse your time, but at this point, one I'm asked, well, how do I construct a witness? You know, because this is all nice and good, but you know, it's not that I can go to a bakery and buy a witness. So how do I get a witness? Well, one thing is that what we are, I mean, it's already written, but it's not out. But it's in this PDF that, if you want, I'm going to send you. If there is a Lie group action by Dirac automorphism, okay, with a corresponding momentum map, then you can extract from this a witness for a good value of the momentum map. A good value is something which is more general than a regular value. And there is here actually an example precisely that shows that you have an example which is not a regular value for the momentum map, but still it's a good value and you have a witness. Okay, so the witness is constructed canonically from an action of a Lie group via Dirac automorphism. And also, and this is something that of course I don't have time to discuss, if you have two concurrent Dirac structures, there is automatically a witness, a common witness that you can extract from them. Okay, so meaning you have your manifold M, you have LM and RM. Okay, so in this case, I'm considering not a submanifold of M, but so you want to reduce directly from M to Y, and you can extract a common witness for these two guys actually, and so now actually we have tons of recipes, too many recipes. So just to give you an idea, one recipe is something like this. You take L, you take the tangential product of L with R, cotangential product with the gauge transformer -1 of L. Okay, so this is a common witness for I mean, actually the projection of this. Sorry, because this is you have to take the projection of this on. Sorry, the projection of this on T. Is a common witness. Okay, yeah, that's the and actually it's not even the projection. Sorry, I'm confused right now. It's actually the intersection. Sorry, it's the intersection with the end of this stuff. So once you have two concurrent Dirac structure, you have a bountiful I would say collection of witnesses. So that's yeah. So I will have other things to say, but you know, I don't want to really to take your time. And then if you want to ask questions, you know, yeah. So thank you for your kind attention.
Thank you very much, Alessandro, for your nice talk. It's a pity that we don't have more time to listen to you because it's very interesting indeed. Okay, is there any question, comment for the speaker?
But I'm going to send you the PDF, so you know you can.
For sure. Thank you very much. It will be very we appreciate it.
So it's not, you know, like.
Any question?
A good one. Do you know if in the presence of the group action, is there any relation of your results with I believe it's singular Dirac reduction by Ratiu, Śniatycki, and Yachts, I believe?
No, I mean, in the sense that here, you know, if you look at what comes after, you know, this is the setup. Everything is assumed to be smooth, you know, like in the sense that there is no singular Dirac reduction here. One might ask if one can use like a stratified space approach, to understand this in more challenging situations, like more challenging in the sense, when you have something singular. But yeah, no, that's not. This is not done in how it is written now. It's not for a singular Dirac reduction or using stratified spaces. Okay. Yeah.
I'm curious, Alessandro, what does it mean, the clean level set? Because I have not met this definition before.
The clean level set simply means that this is a submanifold.
Oh, okay. Okay. So, okay. So more questions? Well, yes, a couple of comments. First, that it's, as I said during the talk, it seems that it has much potential to gather all the theories that there are in the literature. So it could be nice to take a look. Another comment is that he has started with Dirac manifolds, but I think that pretty much this can be generalized to twisted Dirac manifolds and things of the sort.
Yeah, I mean, you're perfectly right. I mean, we actually even started. This was 6 months. I mean, actually, it was last summer while I was in Brazil. We look a bit at the approach that Enrique Burstein, Gilles Cavalcanti, and Marco.
Yeah.
Right?
I know that word. Yeah.
And so, so so here everything is confined in the usual courant algebra, the courant algebroid, where it's just a Tm plus this Rm, right? So, but one, I don't know, so I think one can do it, but that's definitely another, it's not just a tweak, because even things like cotangential, tangential product. So there is all these things that needs to be worked out.
There's a lot of stuff to check. It seems.
No, what I mean, I think it's a good work, but it's not just a new section.
No.
And so what I mean is that one can write a new paper. Yes, that's definitely an interesting point. And the example, I was looking at the PhD thesis of a former student of Enrique, actually, I don't remember his name, and because there is an example in which, starting from the trivial courant algebra, in the sense that you have a Tm plus this and when you reduce, you get something which is not anymore Tm plus this and so there, of course, complicates much more the setup, so to speak, right? Because it's so that's but
okay, I understand. Thank you. Any other comment, Mark? So, Alessandro, once again, thank you very much for your.
Thank you to all of you guys, and I'm going to send the PDF, okay?
Yeah, sure. And if one day you have more things to tell us, you are welcome. You can invite yourself. It's been a real pleasure. So,
well, I might. So you're in Warsaw, right?
Yeah.
So I might visit you, for my sabbatical, if I'm able to move, because now I want to spend time in Italy. So from Italy is not a difficult flight. Yeah.
Listen, okay, so here's one thing. Xavi, you can switch off the record.